study of the project. And I'm presenting a flight technology and test research group activities from the College of Engineering, University Technology, Mara. So, as an introduction, um, we have started collaborating with Hospital Sungai Buloh and our medical faculty, and also a Mission Institute of Transport on their developing drones for medical application. And the first one was began way back in 2014 and 15 when we developed a medical drone for the purpose of sending emergency kit, or basically first aid kit within the campus. And then we got a grant, and we developed it further until we got support from the Futurize Malaysia to develop a commercialized version of the multi-rotor drone, uh, which is, you see here, the white one, which looks like a turtle, flying turtle. That one is used to carry the mobile mini defibrillators, no, it's a word, uh, uh, for emergency supply. But it has a very limited range of maximum 5 kilometers, uh, limited endurance, and also limited payload, which is only around half a kilo to achieve that 5 kilometers. And if you carry about 1 kilogram, then the range is even less. So it's only suitable to be for application within an urban area. So uh, thinking that we have since have some experience on the blended wing body aircraft, which has a very good aerodynamic efficiency, uh, then why not we marry it to and make it as a VTOL takeoff? And in this picture, we have some designs of say blended wing body for flying wing aircraft, some prototypes that we have developed since our research that was, I think, began in 2005, uh, mostly theoretical, and our first prototype was available since 2012. And since 3D printing is getting more mature, and we have explored 3D printing technology to print our drones, our UAV. So we have begun it since around 4 years ago, and now we have some sort of we have quite a steady know-how on it. So basically, we quite confident to have a VTOL BWB version of it for this application. So currently we are developing one under the synergy grant, um, a very simple flying wing BWB UAV for the purpose of field observation by the Malaysian Armed Forces, especially at the Tredarat. We think that why not we just use the platform, the proven platform, and we just turn it into VTOL so that it can carry some payload. So, but the prototype that we have here is only 1.5 meters, so we have no idea how big if you were to carry maximum payload at around 2 kilograms with 50-kilometer radius of action. That we have to send the medical equipment or medical stuff 50 kilometers away from the base, drop it, and come back. And estimated flight duration will be around 1.5 hours to 2 hours. We have no idea how fast it will go, but early estimates should be around 70 to 100 kilometers per hour cruise speed based on its original design. And this shall only be applied to the West Malaysia region, which is would have the maximum mountainous areas around 2,000 feet sea level. So it is mainly fly low, not intended to fly very far. So Methodologically, we begin with the mission profile, like many aircraft design does do. We have to look at the mission profile based on the requirement from the from counterpart in the medical department and the hospitals in the world, and then proceed with the parametric study, gathering around 30 or so available VTOL UAVs around the world, and we proceed with some conceptual design. But actually, the design is already there. It's just that we modify a little bit and resize it based on study, and proceed with the aerodynamic investigation, based on the available wind tunnel experiment data, and modify it to suit for the VTOL condition. And lastly, proceed to performance analysis. And then if we found that they does not meet the mission intended mission specification, then we will continue to do some iteration, going back to the mission profile, parametric study, resize until we get it done properly. So this is the mission profile. There actually originally there is only one mission profile, but we which is the mission one. It simply begins with a vertical takeoff to around obstacle height of 35 feet, and then continue to transition while climbing to around 400 feet, which is legal altitude for UAV for IAA, and fly at the range of 50 kilometers with loss, and then proceed with the unpowered glide until it reaches around 35 feet and drop its payload by parachute. But according to CAN, dropping payload with parachute is illegal. So we also do another mission profile, which is mission 2. The only difference is that once you arrive at the point at the destination, you just have to land. Okay, it will just land vertically, release its payload, and then take off again and go home. That's the only difference. And this is the parametric study done. Total, there are around 30 VTOL AV, and we have dropped around 10, which are probably too big, or not suitable, or do not carry any payload. So we need the data on the payload itself. We need to know how much it can carry and so on. So what would be the wingspan, around the wingspan and the area and so on. So based on the mission profile requirement, we found that from the parametric study, the wingspan of the UAV should be around 3 meters. Maximum takeoff weight around 15 kilos. The payload, we set the payload to be 2 kilograms, and it was found that the empty weight shall linger around 7 kilograms. So that if you were to carry 2 kilos with the FTOW 15, then we have only 6 kilogram provisions for the battery, since it's an electric vehicle. And from there, the expected endurance should be around 2.5 hours, and the cruise speed at around 77 kilometers per hour. I was skeptical around about this expected endurance, but somehow it does not. This UAV does not target to go to have this fly at maximum endurance. Rather, you want to go as far as possible to meet the 50-kilometer requirement. And this is a conceptual design. We resize the original UAV. We add members to mount the VTOL propellers. All propellers are the same. Total, we have around four for VTOL and 1 for cruising. And this is the specification of the conceptual design. And these are all the equations. Not all other equations. I also use these are some summary of all equations that we use for performance calculation. And as for aerodynamics, we relying on the previous wind tunnel experiment, and we repeat that experiment with addition of a VTOL, we call it the strut, okay, the boom that mount the VTOL, addition of that. And to look at how much additional drag that we will get from it. And this is the result, the aerodynamic result. There's virtually no change in the lift coefficient between the VTOL version and the clean version, because so basically the boom that mounts the VTOL motor is quite slim, and I think it does not disturb lift for the time being.
Teresa, you have 3 minutes left.
Done with the static propeller condition. As for CD naught, there is a difference in around 0.01 with the addition of that boom. So I expect the lift to drag ratio to drop. So the maximum lift drag ratio dropped from around 14.7 in the original clean configuration to only 12 with the VTOL. And this surely affect the performance when you plot the power required, power available from the aircraft. As you look at the left side graph, the VTOL maximum speed is reduced to less than 110 kilometer per hour, with clean wings actually slightly more than 180. And the optimal speed for the maximum endurance of power is also reduced to be slightly less than 50 per hour. And we've done this for two altitude accelerations for sea level at 2,000 meters, and we find that there is virtually just slightly increase in maximum speed at higher altitude, and also considerable increase in the minimum power speed. And minimum power speed for the constant power available, that means it's also it's a speed for the maximum rate of climb. For VTOL and clean wing, VTOL has maximum rate of climb just slightly reduced from 1,100 feet per minute to around 50 feet per minute less. And comparison with the between sea level and 2,000 meters for the VTOL, the reduction is more pronounced. And as for the estimation of the ceiling, currently we just look at a linear estimation because we have points. It seems illogical. Okay, basically the electric power motor does not degrade when we increase in the altitude, but the power available from the propeller, since the air density is in higher altitude, that will cause the amount of thrust to be reduced tremendously. I think quite a lot. So in the future, we may look at the other nonlinear estimation. Cannot believe that this UAV can have a ceiling of around between 25 to 30,000 feet, and actually we are looking more like 15,000 feet or less. This is some maneuverability study between the pull-up as the level turn, pull-up, and pull-down maneuver. Just to look at the what is the radius of turn and for various G loads, and below is the NV diagram. It's envelope of this aircraft showing a stall region here with the positive and negative load factor, and its maximum speed, and some caution range, and some structural damage. So this is to be used for to design the wing structure in the near future. And this is actually basically is the structure that has been done for the smaller version of it, but for the large one probably we also want to set this NV diagram to be something like this also. And for the unpowered glide, we are looking at the minimum possible sink rate with the unpowered glide. And as you can see, as you descend between 400 to 35 feet, it gained around 1.3 kilometers. The glide angle around 5 degrees, and that corresponds to the maximum drag ratio of 12. And below is the tall and conventional analysis of landing, strictly to get to the altitude of 55 feet only. And for conventional, it's simply lift off time and taken for it. And based on various performance data that we have and what I presented before, we do some sort of like simulated flight with the mission profile, which is based on spreadsheet, and to calculate the amount of energy that is used for each mission segment, and the result is something like this. I think as many would have agreed that majority of the energy is used for cruising mission. And if you can see the left side, okay, the left side graph is the energy consumption, while the right side graph is the flight distance estimation, and the top graph is for mission profile number 1, and the bottom one is the mission profile number 2. For mission profile number 1, I think you can see that we may achieve a quite a better range than the requirement 50 kilometers, whereas for mission profile 2, it just barely a little bit slightly more than 50 kilometers, which is in this early development calculation, that would mean there's a lot more. We expect a lot more drag from the aircraft. So it in actual condition it may not reach that 50 kilometers because there are other inefficiencies that we may not consider for now for the current stage. So as for energy consumption, we have to understand the reason why mission profile 2 has a lot less cruising range and endurance because it needs to take off and land twice, other than the first mission profile, which is from and back. And
Dr. Rizal, can you finish off in 2 minutes?
yes, this is
okay. Thank you very much.
Right. Okay. Whereas this is the mass endurance and mass range plot taken at the aircraft setting of at maximum top weight, which is not limiting risk. Let's say you want to fly this aircraft with the additional payload of more than 2 kilos, let's say 3 or 4 kilos, but we shall limit the battery capacity, how far we can go, how long we can fly. So this is the plot. So basically, if you're flying around 4 kilograms, you should expect your range to be around half of it. 50 kilometers, not, but meaning that pergi balik will be less than 25 kilometers. So, and if you're trying to fly this aircraft without any cargo and maximum battery capacity, then probably you are looking at the maximum range of around 160 kilometers. With the endurance is around 2 hours. So, meaning that you cannot get the half hours endurance as expected. Okay. And these are the results that we get. And as a conclusion, it is found that this VTOL UAV is probably the performance-wise can enhance this medical delivery by reducing its time because it can prove quite fast. And with the range up to 56 kilometer round trip use of action, and the optimal speed of 77 kilometers per hour while carrying 2 kilograms of medical payload, and a ferry range of 160 kilometers. And would like to thank the RMC of the ITM for providing the grant, and some of our collaborators from the and one of them will be presenting soon. Okay. All right. Thank you very much.
Okay, thank you very much, Dr. Rizal. You can see there was very thorough analysis there. Okay, I now open the floor to anyone who has any questions for Dr. Rizal.
How do I stop the?
Left down there beside the.
Okay.
Go on top.
Can I have one question?
Oh,
Yes.
Yes. Yes, sir.
Dr. Rizal, how are you?
Hi.
I want to ask about the result that you get from the aerodynamic point of view. You done the experimental, or you calculate using the calculation?
No.
The comparison between clean and vertical.
This one. This is experiment one.
Yang mana? Yang biru tu eksperimen?
Yang biru eksperimen.
Oh, yang merah?
Yang merah buat eksperimen juga.
Oh, eksperimen both. You have done all the data that you show is experimental.
Ya, betul. Yang the second one tu I just the same internal model yang ada. Okay, same internal model, I just add the boom kat situ. That's it.
Okay. Really good.
So we have a very small wind tunnel, so the setup time is very, very quick.
But the model that I see is quite big, right? The army, right? The army one that you show, that you modified that from the clean wing. That one.
No, this is not internal model. This is the actual yang fly. Internal model tu kecil je, separuh. Ini internal model. This is not internal model. This is the actual prototype.
Okay, so the clean wing meaning that this is the clean wing with the VTOL with the rotor lah.
VTOL with the multi rotor. That's it lah. I mean, one platform, multiple use. It's easy for us to. Money is also very limited.
Yeah. But it's okay. As long as you do the experimental, is quite very good comparison.
Yes.
Yeah. How the finding? Can we fly the vaccine throughout 5 kilometers? That's your aim, right?
I think we can carry those samples kan yang cik tu. I think boleh bawa 11 kilo. If I resize it to 3 kilo, I can get around 40 centimeter by 40 centimeter of cargo area.
Alright.
That sample kalau ada boleh dah 2 kilo boleh dapat. 2 kilo boleh dapat. So PCR sample kan, sebab nanti you test orang asli kat sana, dia orang asli there, and then lepas tu you come back sample to their nearest klinik kesihatan, and then after that and then you can send the result online. So testing. Thank you.
Okay, thank you very much. So if anyone else have any more questions for Dr. Rizal, I appreciate if you can email him. So now I would like to move on to the next presenter. The paper ID for paper 7, entitled Rotational Speed Analysis on Double Rotating Cylinder for SciFlap using Numerical Method. So I can please have the name of the presenter?
Yeah, I'm Hidayatullah.
Hidayatullah, okay, thank you.
Yeah.
Okay, you may start when you are ready. Sorry, Hidayatullah, your voice is quite breaking.
Sorry, it's due to the internet line. All right. Assalamualaikum and a very good afternoon to the session chair, lecturers, and participants. I, Hidayatullah bin Muhammad Ali, will be presenting my keynotes for the ISAE Paper 7 ID, Rotational Speed Analysis on Double Rotating Cylinder Products, Cylinder Plate Cylinder Embedment SciFlap. So here are the authors, Muhammad Shakir Iman Roslan, me, Hidayatullah Muhammad Ali, and then Associate Professor Azmin Shakrin Muhammad Rafi. Then as in for the affiliations, we are from the Department of Aerospace Engineering. So investigations of rotating cylinder have been studied a long time ago by Sir Heinrich Gustav Magnus, who is a physics professor at University of Berlin in 1852. The experiment was consisted of a brass cylinder held between two conical bearings that could be rotating at high speed by string. Sir Heinrich Gustav Magnus afterwards described the effect by descriptions and called the physical phenomenon by his surname, the Magnus effect. So the probable benefit of this effect compared to the traditional airfoil-based shaped lifting device, such as the aircraft wings, are susceptible high lift coefficients, and therefore the invention on the matter of Magnus has been developed since then. So next, such example can be pictured as the rotor airplanes as per following, since its lifting generation was factored by the Magnus effect. Here shown the applications by the Magnus in the past. On Baden-Baden-Bukau arrived in New York, as shown on the first picture. And then second, in a Conwind company vessel named E-Ship 1. Third, Gerard White concept of rotor aircraft. And then lastly, the Plymouth AA 2004 aircraft in New York. All in all, in this research project, the cylinder flat plate cylinder embedments, or we call in short the SciFlap, is designed referring to the past research work with double rotating cylinder act as the leading and trailing edge for the model, together with the flat plates at the center as the supporting bluff body. Then a 2D two-dimensional flow analysis for various rotational speeds at different cases of rotational direction for both cylinders were tested. The computational fluid dynamics CFD approach were used by applying the 2D simulations with the fluid flow fluence analysis system from ANSYS Workbench 2020 software. Next, we move to the numerical investigation on its geometry and computational modeling. The SciFlap was designed with double rotating cylinder embedded at the leading and trailing edge of the model, with having the flat plate implemented in the center as the supporting bluff body. A gap of 0.005 meter was set in between the cylinder and the flat plates at both leading and trailing edge of the model. This gap was created prior to Abdullah's study, which showed that this arrangement was best for cylinder to flat plate performance. So the SciFlap was consisted of two cylinders with a diameter of 0.16 meter, while the flat plate has a dimension of 1 meter in length and 0.05 meter in height. So the geometry of SciFlap was designed in the analysis system with 2D view. Next, we move to the numerical investigations. And here, the boundary conditions, meshing setting, and solver setting are shown as per following as a preset for the whole study. Antecedent to this, Mentor developed a two-equation Eddy viscosity model, otherwise referred to as the SST K omega turbulence model, which is used in the near wall region to combine and blend with the SST K omega model in the far-field free-stream K omega model. So for the mesh topology, two meshing areas were integrated into the fluent analysis and consisted of an inner zone with a block of 2D times 3D around the model and an outer zone with a block setup of 6D times 15D across the inner zone. The D is the diameter of the total model. So the model surfaces were fixed with y plus less than 1, which was located from the wall to the first mesh nodes, in compliance with the inflation criterion of a maximum of 10 layers with a growth rate of 1.2 to obtain a good results. So now we move to the results and discussions. Here the figure portrays in the effects of SciFlap on its CL and CD, the lift coefficient and drag coefficient at various rotational speeds and angle of attack values accordingly with the velocity stream when both cylinders are rotating in a clockwise directions. In this case, the This case is followed by the Magnus effect theory, in which the flow on the upper surface is the same direction to the rotational direction for both cylinders. Since the velocity ratio falls in between 0 and 2, the vortex shading was formed on both front and rear gap spaces. From these figures, the 500 to 1000 and 1000 to 1000 RPM produce a high lift coefficient at angle of attack 0 degree as per compared with the other two conditions. So however, the 500 to 1000 RPM started to experience partial stall at 6 degree of angle and recovered at an angle of 10 degree due to the existence of 1000 RPM at the trailing edge, which gave extra support in terms of lift to the model, while the 1000 RPM experienced the sudden plateau effect in the CL at the angle of 8 degree and 10 degree. In the CL trends, it shows that different rotational speeds on the leading and trailing edge cylinders has led to an imbalance of the imbalance on the side flap conditions due to the rotational rate. So then the 1000 RPM condition generate higher CL and lower CD amongst others and considered as the most stable condition, which could delay the stall angle up to 10 degree. Therefore, higher angle of attack permitted high Magnus force because of the broad relative velocity towards the rotating cylinder, which have a larger pressure on the bottom than over the upper surface that could lead as pressure recovery at certain angles. So next, here the rotational direction for this case is clockwise and counterclockwise for leading and trailing edge cylinders rotation respectively, with various of rotational speeds as displayed in the figure shown. First, CW-CCW rotation shows that the flow direction on the upper surface for leading edge is in the same directions, but vice versa or opposed for the trailing edge flows, which created a disturbance in airflow and hence caused turbulence above the model surfaces. Consequently, all rotational speed conditions produce negative CL values, which considered as negative lift. It is the drag on the side flap in between 0 degree to 2 degree of angles. The matter may result with nose down forces in some cases. On the other hand, the condition of 500 to 500 RPM produce better CL at angle of attack 4 degrees compared to the other three rotational speeds, which having a lower rotational rate. The model at 1000 to 1000 RPM started to generate lift coefficient at degree of 8, but experienced install when the angle of attack raised until 20 degree. So next, the figure shown the effect of rotational speed at counterclockwise dash clockwise rotation conditions, plus the aerodynamic coefficients and angle of attack are shown. Here, most of them showed a better CL generations at lower angle of attack, but it started to experience a partial stall in between 4 degree and 6 degree. The aerodynamic coefficients of side flap become unsteady at high angle of attack, regardless of high CL. This may be solely due to the rotational directions where the close CCW-CW directions may cause in the existence of reverse lift. It is an increment in drag which resulted with the model to have higher downward force at higher angle of attack, hence resulted with wobbly coefficients due to the inconsistency of the model to sustain its lift at higher angle of attack for different rotational directions. Therefore, a play in rotational directions and speeds may help in reducing the matter arose. So next, the cylinder rotational at counterclockwise-counterclockwise rotation condition was shown on the effects on rotational speed for its CL, CD, and angle of attack. The condition showed that it contrasts with the Magnus effect theory, where the pressure at the top is higher than the bottom surface and thus downward Magnus force is generated. Based on this figure, each rotational speed condition produces negative CL at 0 degree of angle, which shows the downward lift, hence positive in CD. This matter is due to the low lift generation from the CCW-CCW conditions, unlike the one showed in CW-CW rotations, hence resulted with the inability for the model to fly beyond its total weight. However, positive CL at 2 degree was experienced until 8 degree, but it lasts for a very short period of time as the model begins to wobble and unstable onwards. In short, the higher rotational speed at CCW rotation condition has led the drag coefficient for the side flap to increase even more when the angle of attack increases. So in conclusion, the numerical method of side flap of embedding double rotating cylinder at the leading edge and trailing edge of a flat plate revealed that the aerodynamic performance could be produced at all stipulated ranges of angle of attack. The analysis resulted that an increase in rotational speed is prone to rise in the CL of the model. The best condition chosen for the side flap is the clockwise direction for both of them, which satisfied the Magnus effect theory on the generation of lift. The most suitable rotational speed of the model to produce high and sustainable lift is the 1000 to 1000 RPM conditions. This due to the same generation of forces by both cylinders and creates high lift for the side flap to fly and sustains its elevation at prescribed altitude and or conditions. In conclusion, the side flap would be advantageous due to its capability of delaying distal angle, high generation in CL, and low production of CD at high angle of attack. So that's all for today. Thank you.
Okay, thank you very much, Hidayatullah. So now we'd like to open the floor. Anyone who wants to ask any question to Hidayatullah. Anyone? Okay, if there's no questions,
All right,
thank you very much again, Hidayatullah. So I will move on to the next presenter. Okay, the next presenter will be paper 11, Development and Flight Stability Test of an Ambulance UAV. So please give your name, and if possible, if it doesn't affect your internet or your connectivity, please on your video when you present. Okay, so can I have the name of the person who's presenting for paper 11, and you may start when you are ready. Nur Fahimah. Okay, thank you.
Okay, I'll be presenting on behalf of Dr. Wan.
Okay, Fahimah, you can start whenever you are ready.
Okay, one moment. Can everyone see my screen?
Yes, Fahimah, I can see your screen.
Right, okay. I'll start, yeah?
Yes, please do. Thank you.
Good afternoon to speaker, Dr. Dr. Rizal, and the attendees. Thank you for being here. I am Nur Fahimah from VTM Shalam, presenting on behalf of Dr. Wan Malzina. My presentation today is titled Development and Flight Stability for Off and Ambulance UAV. Unmanned aerial vehicle, also known commonly as drone, is being used in many disciplines such as photography, videography, which is either for journalism, film, or promotions. In agriculture, drone is used for pesticide and fertilizer spraying as well as monitoring. Security services that does surveillance, broadcasting, crime scene investigation, or tracking illegal activities. It is used as a visual aid on construction site, wind turbine, power lines, transmission inspection, and many others. It can be used as a part of disaster response for search and rescue, disaster monitoring, relief, and post-disaster assessment. This technology is now increasingly being used for construction across several sectors, especially in medical UAV. In medical discipline, it can be used during emergency response to transport supplies or equipment such as defibrillator. So since the recent coronavirus disease 2019 COVID-19 outbreak, it is compulsory to do social distancing with new law regulations and standard operating procedures. It makes it difficult to do our normal daily activities pre-COVID-19. Contaminated areas are quarantined and locked down to stop spread. Logistical issues due to roadblocks, operating curfews, lack of manpower have made it difficult to source basic needs such as groceries, supplies, hygiene kit, and personal protection equipment. Shop owners and farmers also face great loss when when their goods cannot be delivered. Rural underdeveloped areas lack access to current and true information about the pandemic, and frontliners have higher risk of contracting the virus. For example, personnel working in areas and carry out COVID-19 swab tests will be exposed to the virus frequently, increases their chance of contracting the virus. So, a research that studies out-of-hospital cardiac arrest trends across 7 countries in Asia stated that the survival rate out-of-hospital cardiac arrest is very low, where in Malaysia it's 0.5, Singapore 0.5, and Korea 8.5. There are a few factors affecting survival rate, mainly due to different countries such as poor diet and lifestyle, inaccessibility to medical assistance, or ambulance response time, just to name a few. The average ambulance arrival seen in Malaysia is 17.4 minutes, 7.9 minutes, and Korea 6 minutes. In car cases, victims are susceptible to brain damage and death if not treated for more than 8 minutes, and the likelihood of out-of-hospital cardiac arrest survival rate decreases 10% every minute without resuscitation. The cause for long ambulance arrival is probably traffic congestion and use of illegal driving on emergency lanes that disrupt the ambulance pathway. This study also shows that there are differences in the ratio of ambulance to population in Klang Valley, Kota Baru, and Penang. These differences make it difficult for healthcare centers to be competent when handling emergencies, which lead to an increase in emergency medical service response time. Since Malaysia EMS is developing, there are insufficient study that optimizes the services. It lacks in uniform treatment protocols, system management, communication system, quality assurance policies, and education or training of emergency medical technicians. So basically, low ambulance ratio to population lead to long emergency response time, cause low out-of-hospital survival rates such as out-of-hospital cardiac arrest. Ambulance UAV can bypass traffic congestion to deliver medical supplies and aid first responder on the scene in case of a traffic accident or emergency. It can also equip with an automated external defibrillator to administer electric shock during these incidents. Two-way communication between bystander and physician can be established to provide early assessment and assist bystander on how to deal with the situation before the arrival of anything. The overall purpose of this research is to develop an in-house built ambulance UAV and test it for its flight stability. So ambulance drone is drone equipped with automated external defibrillator AED. In urban area, it can be used to administer shocks during out-of-hospital cardiac arrest. The figure above shows the ambulance drone arriving at the location and the bystander administering the AED to the nearby. This UAV can be deployed alongside emergency medical response and act as a first responder to the scene. If integrated with telemedicine drone, it can provide early assessment and assist bystander on how to deal with the situation before the arrival of EMS team. The pictures shown are ambulance drone by Delft University of Technology, Netherlands. Its deployment is combined with and greatly reduce response time, consequently reduce accident fatalities, brain damage, especially in OHCA victims or patients. As for the methodology, Motor 3 is a 6-rotor multi-rotor equipped with fixed hop flight controller, compass, GPS, and payload relay system. It is capable of smart GPS multi-rotor navigation such as altitude and position hold, autonomous flight, and return to home. The cradle is a right-angle keyboard made of PVC foam board because it is lightweight and easy to design and assemble. On the other hand, the payload release system is made of a single servo that unlocks the opening of payload cradle. The payload cradle is designed to have diagonal bottom so that the payload will fall due to gravity pull. The total weight without payload is 2 kg. The maximum payload that it can carry is 0.5 kg. This diagram shows the structure of NAMTOR-3. NAMTOR-3 is powered using lithium polymer battery. The propulsion system consists of propeller, brushless motor, and electronic speed controller. NAMTOR-3 movement and command is controlled using RC transmitter and receiver by radio frequency. It has an onboard GPS and compass for heading and navigation. Safety switch and alarm buzzer act as a safety system for NAMTOR-3. Payload release system consists of turbo and payload cradle. All of this is connected to PISHOP flight controller running autopilot. The flight stability was tested at a flight speed of 2 km per hour at an altitude of 2.5 meters with no payload. The test was done in outdoor moderate wind condition. 2 sets of flight tests were done. A set of flight tests consists of 15 flights. The initial set of flight tests was to examine the flight stability before modification. The second set was done to test the flight stability after modification was made. Each flight test was precedented with a pre-flight test by checking the UAV response to user yaw, pitch, and roll control. The stability of UAV was measured by observing its ability to stay in a single position during hover flight and by measuring the output motion recorded by PISHOP autopilot system. This figure shows the UAV during flight test. The purpose of the first set of flight tests is to observe the flight stability of initial ambulance design. Initial flight tests shown that the UAV have trouble taking off, and when the UAV is off the ground, the flight is highly unstable. The UAV was unable to hold its position during hover flight, and the UAV pitched forward without user's input, and the UAV was unable to return to its original attitude whenever it was with a wind disturbance. The motion data collected by PISHOP controller in this figure, it can be observed that pitch of UAV grows at a certain point and did not return to the desired pitch. This shows that UAV was unstable. The instability of UAV was seen. The center of gravity of UAV is not centered because of the custom parts used in the initial UAV design. This means that modification needed to be made in the custom parts of the UAV. The custom parts in UAV includes landing gear and payload cradle. The initial landing gear design was shaped from a set of PVC pipes. The new landing gear was used as off-the-shelf standard landing gear with a suitable size for the UAV. In terms of the payload cradle, initial design of the payload cradle used honeycomb plastic planar as its material. This material was changed to PVC foam board, which increases the weight of the cradle by 100 grams. With a lighter payload cradle and landing gear, it will improve the center of gravity of the UAV. I apologize for not having a proper photo of the previous initial design. The issue of vibration in UAV was initially addressed by placing the PISHOP controller on an anti-vibration platform. However, the initial flight test showed that this solution is not enough. The level of vibration from the motor needed to be addressed. The level of vibration of motor was measured by measuring its root mean square RMS vibration with the motor running at 50% throttle for 10 seconds. The vibration was then by fastening a cable along its diameter, and the vibration of the running motor was mounted. So as you can see from the left photo, location of the head of the cable tie and then turn to find the exact location of the motor's diameter needed to be dampened in order to have the lowest level of vibration. Once found, the location was marked and the cable tie was removed, and a series of overlapping vinyl tape was placed to the damping on the motor vibration. As you can see, if you can see on the right photo, this was done for all 6 motors. The result of the modification was tested during the second flight test. The effects of the modification can be immediately noticed with the UAV and have easier time taking off. During the whole flight, it can be observed that the UAV was able to maintain its location with only minor swaying motion. In conclusion, The objective of this paper is to develop a prototype ambulance UAV and test the UAV for its flight stability. It was done with the UAV made from ready-made parts and off-the-shelf controller and a custom-made payload cradle. The initial flight test of UAV has shown that the main source of flight stability of UAV stems from the center of gravity of the UAV and the vibration that comes from it. The center of gravity of UAV was addressed by changing the landing gear and changing the material of the payload cradle to a lighter and more balanced version. The vibration of the motor was improved by rebalancing the motor with a small dummy weight on each of the motor. The result of the modification yield a more stable flight with minimum pilot input and minimum steering motion. The UAV is now ready for further flight performance and effectiveness testing. Thank you very much. That's it.
Okay, thank you very much, Fahima. So now I will open the floor for anyone who have any questions.
May I ask, what is the endurance for such UAV for ambulance use? How long can it fly?
It can fly for 15 minutes.
15 minutes. So if
Yep.
somebody collapse beyond a certain place, you cannot reach it. Now, or 15 minutes, you have to go to that person and come back. So it's about 7 minutes.
It can go for now because it's just a proof of concept. So it can travel 200 meters from a different article, the one that I'm not inclusive in this. So it can deliver item in a 200 meter distance. If it was further, then we probably need a bigger drone. But we can use the same system because our Pilot is adaptable to a lot of sizes, drone size.
One you go for a certain size drone now, you need a PPL, private pilot license. That's the problem.
I'm sorry. Yes, correct. Yes,
So
you're correct. Yes, that's why we couldn't do a bigger one. But if you you can actually go to CIM and ask them for probably a research permit, or and also maybe we have to depends on AM rules and regulation about UAV. So far, I think they are drafting a new policy.
Because I know one university is now making a cargo drone.
I see. Okay.
They're trying to develop to carry 400 kg.
400 kg.
But the leader of the project, that staff, the doctor, he's a private pilot. He have a private pilot license, so he's flying UAV, he's flying aircraft. So he's working on a 400 kg. Then you can carry medical supply. You can carry whatever it is.
True. Yes.
I want to ask you, when you were building the landing gear or the thing, because you have a 6 do you have a jig? Do you build a jig and build it in the middle of the jig, or you just buy tape measurement, whatever it is?
Actually, we just take measurements.
That's where you got the imbalance. That's where you got some. If you have an opportunity or a chance to visit Aero, I don't know whether they do still rebuild helicopters or something.
Yeah.
And they have a jig, and jig is something that a strong frame, frame, where you build in the frame, and all measurement is based from those distance from the frame. Then you your center of gravity will be accurately determined. Of course, the jig was manufactured. You can use theodolite, you can use laser to get your jig right. But once your jig is right, you build in between the jig. Inshallah, your CTD. When looking at this, it's a good idea. But have you compared the performance? If you go to Kedah, they are using drone to spray fertilizer, to spray insecticide.
Yes.
They are not much bothered about CD because as you spray insecticide, your weight becomes less. Your CD, I don't know how they manage to control it.
I think because for the fertilizer drones, because they put the load in the middle, at the center of the CG.
Yeah.
And most of the load is like vertical. It's not it's the what do you call it? Forgot what it's called. The place that holds the fertilizer. They have a tongue. They have a tongue that hold the fertilizer. The tongue is positioned in the middle, like right on the CG. So even if you lose, as long bila you pakai the fertilizer and the fertilizer pun habis, so the CG doesn't change that much.
In your case, you use a landing gear, isn't it?
Yeah.
PVC pipe.
Thank you. Good for the recommendation. I will about the jig that is used in aero for airplanes. So that's a good recommendation. We'll look into it for next.
Not only for aeroplane, I tell you,
Yeah.
when they were building bus body, there was a second batch UTM graduate, the student who graduated mechanical UTM. He worked with a company that made bus coach body, and he now owns the company that makes coach body himself. When he went, the company were making about 8 coach a month. He said, no, we make one every day. And they said, how? He have a friend, another of his classmates who was an Air Force officer who joined Air Force, and he's the one who knew about the jig. Bring him to Aero and see the jig, and he built the jig at the factory, and they build the bus body in the jig. And they will produce 22 coaches every month.
Oh.
This
Quick. Yeah, for rapid manufacturing.
Yes.
So, yeah.
A jig is not for rapid. Now he make luxury coaches. He make luxury coaches, not one a month, even luxury coaches. But still in between the jig, your accuracy of measurement is always there.
All right. Thank you. Thank you very much.
Okay. Thank you very much for the question. Okay, so if anyone has any more questions for Nur Fahima, you can try to email her, get in contact with her. So I would like to move to the next presenter now. Okay, so the next presenter will be paper. Yes.
Yes.
Okay. Paper 24. So Zinria, am I pronouncing your name right?
Zinira. It's Zinira.
Zinira. Okay.
Yes.
So Zinira, you'll be presenting. Okay. So the topic will be micro vortex generator in improving aerodynamic performance of wig aircraft. Okay, so Zinira, whenever you are ready, we start presenting.
Okay. Let me try to share my screen first. Okay. Can everybody see my screen?
Yes, I can see your screen.
Okay. Okay. Hi and good evening. My name is Zinira, and I'm from University Pertahanan Nasional Malaysia. Today, I would like to present my research paper entitled Micro Vortex Generator in Improving Aerodynamic Performance of WIG Aircraft. If you have a trouble to listening for me, please let me know. Okay. So this is the presentation outline that consists of research background, problem statement, research objective, significance of study, literature review, research methodology, result, conclusion, and references. So for the research background, what is a WIG aircraft? WIG aircraft is wing in ground aircraft, or we call it as ground effect vehicle. Is the vehicle that use the ground effect as a lifting system to increase the lift to drag ratio by cruising just above the water surface. So this is the comparison of flow characteristic between aircraft at altitude with aircraft near the ground. So for the aircraft at the altitude, the vortices will fully develop at the wingtip, and this condition will lead to the increase in drag coefficient in order to generate high lift. So in order to overcome the drag coefficient, we need higher thrust to move forward. So in comparison with the aircraft near the ground, the vortices at the wingtip were being compressed and dissipate due to the ground effect. So this condition will lead to the decrease in drag coefficient and eventually increase the lift coefficient, and we only require low thrust to generate lift. And this is the benefit of WIG, or wing in-ground aircraft, which is it offers safer flight operation compared to the aircraft at altitude, and then it offer better fuel consumption and better cruising speed because we generate less drag coefficient compared to the aircraft at the altitude. However, at the recent study, very recent study, has claimed that the step at the hull fuselage here tend to induce significant backward-facing step while cruising. BFS happens due to the sharp edge geometry at the fuselage step that leads to flow separation, reattachment, and unsteadiness in flow field, which eventually cause deterioration of aerodynamic performance. Hence, this problem leads to this research objective, which is to investigate the effect of passive flow control towards the drag coefficient at the backward-facing step area. So from this objective, we provide the significance of the study, which is this passive flow control with optimal design are beneficial to reduce the formation of CD. And then by using this approach, we can offer low cost, economical, and practicability in application of WIG can be achieved. Then this approach also can be useful for better WIG design in future and the production aircraft industry. So this is the previous study that involved in flow control. To control the flow separation, there are two common methods that has been introduced to control the flow separation, which is active flow control and passive flow control. So for active flow control, the common method used are plasma actuator, blowing, suction, and synthetic jet. And for the passive flow control, the common method introduced are Vortex Generator that consists of ram or vane and leading edge bump and slot to control the flow separations. However, based on the published literature review study, most of the study being introduced only focus on controlling backward-facing step at over an airfoil or wind turbine, and until now, only a few researchers has been investigate this method thoroughly in the context of WIG. Okay, so this is the method of the experimental study. The first one is WIG fuselage design. So this is the design of the fuselage, and there is a slot extruded for the interchange of MVG. And to design this the fuselage, we identify the suitable dimension of WIG based on the previous study, and then we design it using CAD software, and then proceed to the fabrication of WIG and post-process, perform drag tests, and finally validate the data with the previous study. Okay. The next one is to perform drag tests using post balance. So this is the fuselage, and the flow direction is from here, and this is the ground plane, and there is a rod here insert into the fuselage, so that the steel rod with the WIG model can that was inserted to the force balance to generate drag coefficient data. And then the fuselage here will be subjected to different velocity, which is ranging from 0 meter per second to 10 meter per second, which is equal to Reynolds number 2 to the power of 4 to 2 to the power of 5. Okay, the next one is micro vortex generator design. So this is the slot dimension design, and then this is the ram dimension design conducted in the study, which is the chord length and the width is fixed to 13.42 millimeter and 10.92 millimeter. And then the testing parameter that will be varied is ram height and the angle of attack, with the ram height is chosen based on the boundary layer height that we get from testing the plane fuselage. So the angle of attack, this is the ranging that has been recommended from the previous study, which can offer better lift coefficient. And this is the wind tunnel facility in University Pertahanan Nasional Malaysia. The operating condition is between 0 to 100 meter per second. However, due to the current concern of electrical shortage, we limited the operating speed to 0 to 50 meter per second. And then the test section length is 0.3 times 0.3 times 1. And then the equipment tested to get the drag force is 3 component force balance. This is the result of the baseline cases. So based on the result, there are 2 flow characteristics formed as the Renouf number increases, which are laminar flow and turbulent flow. For the laminar flow, it happens between 2 to the power of 4 to 6.1 to the power of 4. And then for turbulent flow, it happens between 8.1 to the power of 4 to 2 to the power of 5. And this is the separation point that occur at 6.1 times 10 to the power of 4, and the reattachment occur at 1.1 10 to the power of 5. So laminar region is where the flow experience boundary layer separation, which leads to flow separation and increase in drag force. So when the flow reaches the critical Renouf number, the screen friction viscosity become less dominant because the flow no longer in contact with the surface, which explain the steep drop of CD. As the flow exceeds critical Renouf number, the flow energy trapped at the bottom of the step corner mixing the energy at the recirculation zone and result in increase in CD. And then after the reattachment, the screen friction in contact again. The flow is in contact again with the surface, which explain the small change of CD here. So this is the effect of micro-ram angle. So three angle has been tested, 12, 16, and 24, and it appears that 16 degree is the best configuration to produce higher vorticity in order to reduce drag significantly compared to other cases. So compared to the baseline, the percentage reduction is about 43% in the laminar region here and 20% in the turbulent region here. So this is the effect of micro-ram height, which is vary from 1.068, 1.864, and 1.9805, and the base height is identified for 1.864 millimeter. So it appears that compared to the baseline, 42% decrease of CD at the laminar peak and 20% decrease at CD at the turbulent region. And then this happens because this height is able to generate stronger streamwise vortices compared to the other cases, which thus developing a complete boundary profile to pass through BFS location with less reattachment. Consequently, the drag reduction were noticed. So this is the conclusion of the study, which is to determine the capability of passive flow control device known as micro-ram in reducing drag coefficient over WIG fuselage, specifically at the BFS area. The MVJ with 16-degree angle and 1.864 millimeter height were the best configuration to produce minimum induced drag. This is due to the effectiveness of the flow control to minimize the reattachment length in separated region caused by sharp edge geometry at the fuselage. And for future work, it is recommended to investigate this angle and height thoroughly in wide range, because this study only involved in three measurements. So and we also suggest to investigate the effect of interspacing, since it is claimed can reduce the flow reattachment at BFS location. That's it. Thank you very much.
Okay, thank you very much, Zinira.
Mm-hmm.
Okay, so now I will open the floor for anyone to have any questions for Zinira.
I have a question.
Yes.
All right. What is the scale of your model, internal model, compared to the actual size of the wig craft?
Okay. For the scale, it's actually it depends because we have a very small test section. So we try to scale down as much as possible since
No, what I mean is,
mhm,
I when I first look at the picture, early picture
yes,
of the
uh-huh,
wig aircraft, it seems that you are working on the airfish design.
a fish design.
Cool.
Okay.
Airfish.
Mm-hmm.
Okay. What is the scale of your model compared to the airfish?
Compared to the a fish, I might need to check again
One
for
ten,
the.
because it seems you seem
Mm-hmm.
that you have a good result here. With
Yes.
16 degree angle set up with 1.8
Mm-hmm.
millimeter.
Mm-hmm.
But when we apply to the actual aircraft,
Mm-hmm.
then will it be valid? We just simply scale it up, because
Yes.
when the aircraft is larger, then you have a different Reynolds number there.
Mm-hmm. Mm-hmm.
Okay, because you're looking at Reynolds number between 10 to the power 4 until 10 to the power 5.
Mm-hmm.
Probably the actual aircraft is operating at the Reynolds number of 10 to the power 6
Yes.
and 7. Maybe a weak aircraft is not that fast.
Mm-hmm.
So probably at 10 to the power 6, not
Mm-hmm.
more than 10 to the power 7. So
Mm-hmm. Yes.
will it be valid then to have the 16 degree and 1.8 millimeter setup? I mean, even if you scale up
Mm-hmm.
10 times, it'll still be 16 degrees, but then another one will be about a 18 millimeter.
Mm-hmm.
So will it be valid then? Can you present this model to the actual one?
Mm,
Yes or no?
yes.
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 Are you sure?
Okay, I repeat your question again because I'm kind of
Let's
not
say
answering.
you have
Okay.
your model represent the 1/10 scale of the actual
Okay.
aircraft.
Okay.
Okay.
Mm-hmm.
Now you're doing it. You're studying at a maximum of 50 meter per second, probably representing a certain Reynolds number, and
Mm-hmm.
then now your study limits between 10 to the power 4 Reynolds number in the order of 10 to the power 4 and
Mm-hmm.
until 10 to the power 5.
Mm-hmm.
Okay. Now, if you apply the same design, just you scale it up to the actual
Okay.
size of the aircraft,
Mm-hmm.
will the 16 degree and 1.8 millimeter, if you scale up, will become 18 millimeter. Okay. If you scale up 10 times, it will be 18 millimeter. Will 18 millimeter height
Mm-hmm.
still be valid for, will give you the performance for the actual size of the aircraft?
No.
Ah. uh,
Okay.
It's actually a good question,
so
which is
basically,
I will check.
purely academic study. Yeah.
Mm-hmm.
Yeah, you have to check. If you were to
Yes.
apply this, then uh, do you have any idea why is the shape of the body is like that? Why do they have that flat, uh, flat shape behind the under the belly of the fuselage?
You mean the step?
Yes.
Yes.
If I'm not mistaken, it's good for the braking, maybe.
Okay.
I think that question you should ask a marine engineer, because this is not classified as an aircraft. An airfish is classified as a ship.
Yes, I am.
So
Yeah.
this is it has a body of a flying boat.
Yeah.
Yes.
That's the reason why it is like that.
Break away the wave that hits the body.
Yes, exactly.
Okay, can I join in? It's
No
very, very
question.
interesting to talk about wigs. It seems that the only country that is promoting wigs before is Russia, but I don't know how they do it now, because they were trying, and they even called the Caspian Sea monster or something. They built one big one.
Prof. Afifi, it is called Ekranoplan.
Yeah, I know, but wig was Russia was promoting it, but it didn't catch on with other countries in Europe.
Yep.
One thing is maneuverability. Maneuverability of wig is poorer than aircraft, because when you depend on the ground effect for your lift, so to maneuver it is not it's not as easy because as maneuvering an aircraft, and they have to make that shape, that shape of the boat with the strip that is just to break the wave. Now when it's landing on water, the wave will hit the hull, and you have to split. I mean, when you look at the design of high-speed boat will have that strip also. That's why they have that strip, and that caused that problem with the vortex and so on. But it's interesting you're still working on it. I just want to ask the speaker, are you joining the Navy or the Air Force when you graduate?
Sorry?
Will you be joining the Navy or the Air Force when you graduate?
I hope I can. Yeah.
Because then the Russian were promoting for the Navy, but it didn't take on because of maneuverability. It's considered safe, but maneuverability is very, very poor compared to even a ship, a boat, a high-speed boat.
Mhm.
So when you're doing a testing in wind tunnel like this, the
Mhm.
scale ratio have to be right. If you have wrong scale ratio, then because when you reduce the scale, you
Mhm.
have to have a higher velocity to get the same Reynolds number.
Mhm.
And the big thing, you have a lower velocity unless
Mhm.
you do the testing in a water tunnel, because the water have a density 1,000 times air. Then you can do a much lower speed and you get the result.
Mhm.
So when you do in air, my experience when I was teaching UTM, we did the similarly, but for Sikorsky, for Nuri helicopters. Okay, they were having a problem when Nuri helicopters they used Nuri helicopters to deliver about the boat that is used by the military, or what we call that boat. The boat that is used for the military to patrol. When you suspend it under the helicopter, at a certain speed, the boat starts swinging. Certain speed, it swings forward and backward under the helicopter. At certain speed, it swings left and right. So finally, why not we model in the wind, but we cannot get a proper result because of the scale ratio.
Mhm.
Scale ratio. We made a hull of the Nuri, and we make a model of the boat, but the scale ratio is not. But we can still demonstrate a swinging effect of forward and backward, and so that's the problem when you have a small wind tunnel.
Mhm.
We have a very
Yes.
small model, all the Reynolds number is output.
Yes.
Thank you.
Agree. Mhm.
Okay, thank you very much.
Okay.
Okay, thank you, Zinira.
Thank you very much too.
Okay, so we now move on to the next presenter. Balaji, is it? Are you there, Balaji?
Yes, sir.
Okay, Balaji, whenever you are ready, you can start presenting.
Okay, sir. I'm ready, sir. I'm ready to share my presentation.
Okay, you go ahead and thank you.
My screen visible, sir.
Oh, sorry, I cannot see anything yet.
Now I have shared, sir. I have shared the screen.
It's not coming
Now,
up on
okay.
me. Okay, now it come out.
Oh, thank you, sir. Thank you.
Yep. Okay.
Good
Okay, please proceed.
Good afternoon to one and all. I'm Dr. G. Bolaji. My conception of NREL 809 airfoil with Vertex Generator. My teammates are Mr. Mutram and Dr. V. Madan Raj. Okay, this is my outline of my presentation. First is introduction, objective, literature survey, experimental methodology, research and discussion, and summary. Next, in the introduction, the Vertex Generator. Okay, Vertex Generator is one of the passive device that also we can call the aerodynamic device. Consists of the small van usually attached to the lifting surface. Okay, lifting surface such as airfoil or aircraft wing, or in case of wind turbine, it will be placed in the wind turbine blades. Okay, that attached to the it will be attached on the body so that we can control that flow, control that fluid flow, so that we can enhance the aerodynamic performance of the airfoil. Now we can see this right side of the picture. You can see the right side of the picture without there is no that this is a blade, the turbine blade, and near to that after the midsection of the blade, near to the tip of the blade, the flow leaves smoothly in that tip, and near to the hub of the blade, the flow gets separated so that the performance, the lift coefficient drastically reduces. Okay, once the flow is separated, the flow it will be that lift coefficient will be reduces. Okay, then in the next left side, you can see this. Once if you attach that Vertex generator, we can get the smooth flow. Okay, smooth flow. That means the attached flow happened because of the Vertex generator provided on the quad end of that aerofoil. This is so that we can get the more performance that more in the wind turbine. In other case, in aircraft, we can get that better so that we can get higher lift coefficient in case of the aircraft and the other aircraft body. This what happened now, actually the Vertex generator having lot of various configuration. Here I am going to use that triangular Vertex generator and the rectangular Vertex generator. This I am going to used in the airfoil. What is the effect of pressure? Okay, what is the effect of pressure if I am going to use the Vertex generator on the over the airfoil? That I am going to investigate in our studies. Then here in other applications in the aircraft, you can see this the control surface such as the flap, elevator, and aileron, and rudder, and the wind turbine blade. It can be used so that we can improve the aerodynamic performance. Next slide is
Dr. Balaji, is your slide moving or still is the first slide?
No, okay, sir.
Because I can see that is your slide is not moving. Okay, now it's moving.
Yes.
Okay, sorry about that.
What,
continue. I thought you were moving your slide. Was you moving your slide?
Yes, I have changed the slide, sir. Now now it's in fourth slide.
Okay, sorry. I thought you changed your slide. Okay, thank you. Sorry then. Continue. Please continue.
Okay, sir. Shall I proceed, sir?
Yes, please.
Okay, sir. This is where are the base we are using the Vertex generator. You can see that the left side of the aircraft. Okay, here the upper surface of the aerofoil, the blade, the wing, the Vertex generator is placed there, so that we can. This is the place they are using. Other application, we can see this here, the right side picture of the wing. Here you can see this near to the leading edge, that Vertex generator is okay. The rectangular type Vertex generator is placed so that we can control the flow. Suppose another picture, okay, if you are not using the Vertex generator, what is the flow behavior once we are changing the angle of attack? In the first case, the zero angle of attack, without the Vertex generator, the smooth flow, and if you are increasing the angle of attack, the flow separation, the boundary layer separation begins to separate. Once separation is done, the flow will be like that, okay, so that we will get the stall, okay, wing stall. If you are attaching the Vertex generator, we can see that if we are increasing the angle of attack, we can get the smooth flow, so that we can get the better aerodynamic performances. So that we are using the Vertex generator. And in other case, wind turbine also we can use the Vertex generator. This is our introduction part. Next one is objective. Okay, my objective is to study the pressure, investigate that Vertex generator on NREL S809 aerofoil in aerofoil to understand the aerodynamic characteristics. Okay. The another one is another objective is to understand the pressure distribution over the S809 aerofoil with and without the triangular and rectangular Vertex generator. This is my objective of this work. Another one is literatures. Okay, I have referred so much literature. Here, the first literature is experimental study of influence of Vertex generator on aerofoil for wind turbine. Here it is observed that here they have taken the 3 different aerofoil. They have used that Vertex generator over the aerofoils. They have the performance will be they got that better performance if you are using the Vertex generator. That will be observed in this literatures. Another literature is the numerical investigation, the prediction of effect of Vertex generator on the aerofoil performance. Okay, this is they have done the Vertex generator using that on the over the aerofoil with the CFD simulation. That dimension is given here. The Reynolds number also, which is given 3 lakhs Reynolds number. Next one is this is a figure they have used. This is a configuration they have used. Then next one is third one is the effective improvement of wind turbine generator by introducing Vertex Generator. Here they have studied that a lift coefficient with the Vertex Generator and without the Vertex Generator. That study has been done. Without Vertex Generator, they are getting the CL value of 0.3269, and with the Vertex Generator, the 0.439 the lift coefficient. So that if you are providing the Vertex Generator, we can get the better performance. It's proved, the paper proved that. The next one is next one is the aerodynamic shape of Vertex Generator. Okay, the various geometry changes also. By doing the geometry changes, we can enhance that performance of the that is control surface. Okay, that has been done in this paper, the 5th paper, and another one is some other literatures. Okay, that is put up in that tabular column. The first paper published in 2016. That the title is "Effect of Vertex Generator on Aerodynamic Performance of Thick Wind Turbine Aerofoil." Here they have done that uncertainties measurement. Okay, that will be investigated in this first one, and the second one is done by the Stoney et al. The title of the paper is "Design of Noco Series Aerofoil for the Wind Turbine." It's published 2013. Here they have done the geometrical model developed take the different shape and size with the help of associated parameter. Okay, they have done that by studying that they have designed that aerofoil. Okay, aerofoil with the Vertex Generator in this paper. The next one is that the effect of sub-boundary layer Vertex Generator on incident turbulence. This title is published in 2003. Here, that the micro vehicle Vertex Generator has been investigated. The result investigated. Okay, the flow velocity of the has been and the wake region also investigated in this paper. Then 8th, 9th paper is in experimental numerical analysis of effect of Vertex Generator, Vertex Generator height on vertex characteristics and the aerofoil aerodynamic performance. Okay, published in 2019. They have done that a characteristic of Vertex Generated by VG. Okay, that investigation has been done in this paper with the delta V. The next one is that effect of Vertex Generator on printed trailages and flow characteristics of flow characteristic study of wind turbine blades with the Vertex Generator has been also been okay, I have referred for so much. I have referred for my research work. Then now I move on to the experimental setup. Here, the experimental setup I have used that subsonic low speed subsonic wind tunnel. This is the test section size is 600 mm cross 600 mm cross 2000 mm. Okay, with the breadth length of the test section I have used. The maximum speed attained in the test section is max wind velocity attained in the test section is 50 meters per second. The block edge ratio has been estimated by fitting that my model less than 5%, and turbulence also calculated. And the Reynolds, I have used the two different velocity for do my investigation. One is 12 meters per second and 20 meters per second. For that, I have calculated the Reynolds number as per the geometry dimension. Okay, 32 into 10 to the power of 3 and 56 into 10 to the power of 3. This is my Reynolds number. These two Reynolds number investigated on my model. Then I have used that model geometric model design. I have used that AutoCAD for my design of the aerofoil. Then this is my geometric model. Okay, geometric model. I have drawn it on that AutoCAD. That chord length is 200 mm, and thickness of the aerofoil is 42 mm. This is the data which is get it from the NREL. Based on this, with respect to my wind tunnel size, it has been designed that drawing and that the wind turbine has been designed. The S809 aerofoil is designed, and this is the location. Okay, here that you can see this right side, the spacing parameter. Okay, this is here I have used two different kind of Vertex Generator. One is, as I told you, the rectangular Vertex Generator and the triangular Vertex Generator. The distance between the two Vertex Generators, the oblique angle is placed there. The distance you can see that the distance between the spacing between the two Vertex Generators and D, and pitch is 100. Okay, the pitch is represents 100 P, and the distance is 100 mm. Then it is located at the quarter point of the chord. That means quarter chord point of the aerofoil. Then this is the arrangement. This is the model I have fabricated using the teak wood. You can see this picture. The dimension also given in the picture. Here that S809 aerofoil is fabricated with the teak wood, and that rectangular and Vertex Generator is placed over the aerofoil at the chord point of cut point at the distance of 50 mm from the leading edge. This is the two different variety of vertex generator I have used for my work. One is triangular vertex generator, and another one is rectangular vertex generator. I have not changed the geometry of the vertex generator to study. The same geometry only I have used, same dimension and geometry has been used for my studies. Then next one is these are the case study I have made it to my wind tunnel. First one is the aerofoil NREL S809, and first case is without vertex generator. With the plain without vertex generator, what is without vertex generator and triangular vertex generator and rectangular vertex generator for 12 meter per side, and I have measured the pressure between 0 to 25 degree angle of attack. Similarly, I have done the another case is without vertex generator and triangular vertex generator and rectangular vertex generator, the velocity of 20 meter per second and angle of attack vary from 0 to 25 degree. This is my this is the case study. This is a picture I have taken when I kept that model in the wind tunnel test section for 0 angle of attack and 5 degree of angle of attack, and 10 degree, 15 degree, 20, 25 degrees shown in the picture. The results are taken. Here I have taken the pressure distribution. Here in this study I have done only the pressure distribution, effect of pressure distribution of the S809 airfoil without vertex generator, with the vertex generator. The first case, the first one is pressure distribution of S809 with the vertex generator of 12 meter per second velocity. You can see the pressure distribution for the different angle of attack. It's plotted in the figure A to F. The effect is drawn, and the pressure distribution effect is drawn, plotted in the graph. We can see this for lower velocity, the pressure distribution uniformly varying from picture 1 to A to F. Okay. Then in this we can see this some places having the more pressure distribution at the trailing edge of the vertex generator because of the it is received from got it from a rectangular vertex generator. And without vertex generator and triangular vertex generator have the little significance compared to rectangular vertex generator that will be observed in this study. We can see this is a picture A for 0 angle of attack and pressure distribution, and another one is angle of attack 5 degree, another one is angle of attack 10 degree and 15 degree, and the next slide is 20 degree and 25 degree. Okay, that is drawn. This is for 12 meter per second. Another case study has been made it for 20 meter per second. The same with the vertex generator, without vertex generator. Okay, with the triangular vertex generator. But if you are increasing the velocity of the flow in the test section, that it is observed that pressure distribution variation is very significant and have drastically varying from 0 to 25 degree. That has been plotted in the graph, and this is one of the things is observed. And why? Because of the actually we know that if you are replacing the vertex generator, it get the flow, once the flow pass on the vertex generator, the flow get accelerated. That will cause that pressure deviation on the trailing edge of the aerofoil. Okay, that will be observed. Okay, if you are increasing the angle of velocity, that will be more. The pressure variation will be more compared to low velocity. This is the observation I have is observed in this my investigation. Then this is my summary. The experimental investigation of pressure coefficient of the S809 aerofoil profile plate with and without triangular without and with the triangular rectangular vertex generator is at different velocities investigated in the subsonic wind tunnel, and it's observed that the vertex generator can considerably improve the aerodynamic characteristics of the aerofoil, enhancing the pressure coefficient by delaying the boundary layer separation. And another one is for low angle of attack and low speed, there is no much deviation of pressure with the help of deviation with the help of triangular and rectangular vertex generator. At higher angle of attack, there is noticeable variation in the pressure coefficient when compared to triangular and rectangular vertex generator, and drastic variation also observed when the pressure coefficient when we use the rectangular vertex generator, which is compared with the triangular vertex generator. And experimental study of pressure distribution of aerofoil, of cambered aerofoil with and without vertex, that plot has been made in this study. Okay, then this is my summary report, and these are the reference I have used for my this small work. Okay, only the part of work only presented in this conference. These are my reference. Thank you.
Okay, thank you very much, Dr. Balaji.
Thank you, sir.
So now I open the floor again to anyone who wants to ask questions to Dr. Balaji.
Okay, sir.
Anyone? Okay, if there's no one that wants to ask a question, I thank you again, Dr. Balaji.
Thank you very much, sir.
Okay.
Thanks for the opportunity to the coordinator and all of you.
Okay, thank you again. Okay, so now I would like to move to the next presentation. Paper ID 37, numerical analysis on the effect of longitudinal placement of vortex generators for jet control. So I would like to invite, I think the presenter is Balamani. Are you there, Dr. Balamani?
Yes,
Okay,
yes, I am.
Okay, Balamani, whenever you're ready, you can start presenting.
Yeah, is this PPT visible?
Yes, I can see your PowerPoint.
So, good afternoon to everyone. So, my paper ID is ISAE paper 37. So, I'll be presenting my paper titled Numerical Analysis on the Effect of Longitudinal Placement of Vertex Generators for Jet Control. So, I am a PhD scholar working under Dr. Panigarsu sir. So, he is my supervisor at Madras Institute of Technology, where I am doing my PhD part-time. So, the abstract of this paper. So, the essence of the paper is that this is a numerical study. It is a simulation. It is about passive control of jets using longitudinal placement of vortex generators. So, here 6 triangle-shaped vortex generators are placed inside the nozzle, and the effect of vanes on the jet decay and spread characteristics is studied. The study was carried out for operating conditions of Mach number 0.4, 0.6 and 0.8. The petard pressure was evaluated along the jet center line and along the radial distance from the nozzle exit to capture the potential core region of the jet immediately downstream of the nozzle exit. So the central line petard pressure decay, what it shows is it is a measure of jet propagation, while the radial decay is a measure of jet spread. The faster the decay, the faster is the jet mixing with the entrained fluid and so on, and thus indicating the mixing of ambient fluid mass entrained at the jet boundary with the mass of fluid inside the jet. So the results were compared with a plain circular nozzle, which will be called as base nozzle hereafter. So plain circular nozzle is without any vortex generators, with the same dimension and at the same operating condition in order to quantify the effectiveness of the vanes. And it was found that the nozzle with the vanes was able to reduce the potential core length compared to the base nozzle, and thus enhancing the mixing characteristics of the jet while it producing minimum thrust loss. So I will explain further upon this. So before we go into the details of the paper, I want to give some introduction about the concepts. So a jet, it may be defined as a continuous fluid which is issuing from an orifice into a medium of lower speed fluid. So here in my paper, what I have considered is a jet is existing from the nozzle into the ambient air surrounding stationary air. So as the jet travels further downwards, that is towards the downstream, okay, it slows down because of mixing with the stagnant ambient fluid, and this ambient fluid is getting entrained into the jet. So this is due to boundary layer at the nozzle exit, which develops roll-up structures or ring vortices. You can see that in this picture. Okay? So the jet comes out of the nozzle, and as it interacts with the ambient, there is a formation of vortices, and as you go further downstream, the formation of vortices increases and the size of the vortices also increases. So how this takes place is explained here by a small animation. So the jet, okay, you have a white layer, right? So that is the boundary of the jet. So that layer slowly gets distorted because it is mixing with the atmosphere air. That is, the ambient fluid is getting entrained into the jet. So slowly vortices are getting formed, and as you go further downstream, the size of the vortices increases. So here the mass flow to any cross section of the jet progressively increases along the downstream direction. So hence, to conserve momentum, the centerline velocity decreases with downstream distance. Okay. So basically the jet profile, that is a jet which is coming out of any nozzle. So here I've considered a convergent nozzle. So I'm considering convergent nozzle and I'm considering subsonic jet. So that is below Mach number 1. So, but mainly I'm concentrating on Mach number 0.4, 0.6 and 0.8. So for that, the jet profile will be like this. So you have a center region called as potential core. This triangle shaped region, cone shaped region, this is called as potential core. So this is the region where the jet velocity will remain constant. Jet velocity will remain constant, so that similarly the total pressure will also remain constant. So as we go downstream, okay, so this velocity decreases because, as I explained earlier, the ambient fluid is getting entrained into the jet. So obviously the velocity decreases, and as you go further and further downstream, you have a region where the velocity is same throughout the jet and it is decreased to atmospheric conditions. So it can be defined as the jet can be categorized into 3 different regions. So the first region is potential core region, where you have the velocity constant up to the potential core region. After that, there is the developing zone, or it can also be called as transition region, where the velocity starts decreasing. It is no longer constant value, it is decreasing. And after that, you have a fully developed region where that is wherever you measure the velocity along the jet. Okay, in whichever location you measure, you will get the same velocity. The velocity has decreased, but throughout the jet, you have the same values for the velocity. So here, this region is called as fully developed zone. So this is the typical profile of the jet. So here the y-axis is P by P naught, meaning the total pressure outside the nozzle along the center line. Okay, the total pressure is measured from the exit of the nozzle along the center line, and divided by the P naught is the inlet pressure. Okay, the chamber pressure or the inlet pressure of the nozzle, and axial distance x by d. So x is nothing but the location from the exit of the nozzle along the downstream, and d is the exit diameter. So here the values have been non-dimensionalized. So that's why we are having P by P naught and X by D, so that we can compare the profile with other methods. So this is the basic profile of a subsonic jet. Next, control of jets. So why we need control of jets? So basically control means the ability to modify the jet flow mixing characteristics to achieve engineering efficiency, technological ease, economy, adherence to standards, and so on. So there are many methods of control of jets, and we need to know why we need to control jets. So the advantages is that by enhancing the mixing process or by increasing the rate of mixing, okay, you can increase the efficiency of a combustion cycle. Okay, so this is not particularly to a nozzle flow. This is in the case of combustion, but the same concept applies there also. And when you're considering a flow from the nozzle, okay, the infrared radiance of the plume or the jet which is coming out of the nozzle can be reduced. Okay, and the jet noise in the case of supersonic or transonic or hypersonic flows, obviously those are flows which are characterized by high noise, right? So by increasing the mixing rate of the flow jet with the ambient fluid, the noise can be reduced. So the same concept which I'm here discussing for subsonic jets can be extended to supersonic and transonic jets also, and it can be extended for combustion also. So there you'll be considering air and fuel mixing. So the concept can be applied to various areas. So in control of jets, we have different methods. Here I am dealing with passive control. So passive control, it usually means geometrical modification of elements from which the flow separation occurs. Okay. So if you see here in the right side, you have a diagram of different nozzles. These are the most commonly used passive control method. Okay, at the exit of the nozzle, here you can see a small square-like structure. So these are called as tabs. Okay, so you will have tabs at the exit of nozzle. What these tabs do is it creates additional vortices. So vortices are something which gets the ambient fluid into the jet. So by getting the ambient fluid into the jet, you are increasing the mixing process. So these tabs help in that process. Similarly, you have grooves. Grooves are nothing but a hollow region at the exit of the nozzle. Okay, and you also have, these are called as notches. This is also a hollow region, but in a different shape. Okay, so what it does is it introduces more vortices. It creates vortices. It creates pressure difference, and because of that,
Balamani,
yes.
you have 5 minutes left. So if you have a lot to present left, I will advise you to go to the.
Okay, I'll go
okay.
quicker.
Thank you very much.
So yes, so these are some of the main methods of passive control. So I'll just quickly go through the literature review. So in literature review, mainly what I wanted to point out is, so far all the literatures are about the vertex generators which are placed perpendicular to the flow. So if you see here, so these are perpendicular to the flow, right? The flow is in this direction, so it will obstruct them. In case of longitudinal placement, you have grooves and notches, but are hollow surfaces. There is no any geometry placed in the longitudinal directions. So as my time is limited, I'll just tell you what I wanted to point out from the literature review. So in all these literature reviews, about 80% of them concentrate on vertex generators which are placed perpendicular to the flow. So they are going to obstruct the flow. So whenever you're obstructing the flow, the disadvantage is that your thrust is going to get reduced. So you will have thrust loss. So that is not a desired result. Even though the mixing process is being enhanced, you do not need thrust loss. Okay. So so in case of longitudinal placement, there is no any geometry or structure placed longitudinal. Okay, they are only the research is available for only hollow surfaces in the longitudinal directions. They also enhance the mixing process, but they also yield some thrust loss. So what I propose, or what this paper deals with is, we are going to deal with the longitudinal placement of the vertex generators. So expecting that it is not upsetting the flow, it is only going to deflect the flow. So thus the thrust loss will be minimum or lesser than the other methods. So this here we have the nozzle design. So this is a convergent nozzle, and you have these are the vertex generators placed at the exit. You have 6 vertex generators. So they run for 10 mm from the exit, and the width of the vanes are 2 mm and the height is 1 mm. So the computational domain, you have, so this is the nozzle. Okay, so I've taken the computational domain. The length of the domain is of 30 times the length of the nozzle, and the height of the domain is 15 times the exit diameter of the nozzle. So the boundary condition, so this is the inlet of the nozzle is given as inlet, and the end of the domain is given as outlet, and the surrounding surface is given as far field. Okay. So basically, in order to ensure accuracy, we perform grid independent study. Okay, because the grid should not affect the results. So 3 mesh models with 15 lakh cells, 20 lakh cells, and 25 lakh cells were considered, and it was found that the cells, that is the mesh with 20 lakh cells and 25 lakh cells, were almost matching, and thus the grid with 20 lakh cells, that is here the medium grid, was chosen for the analysis. So this is the center line pressure decay. So the center line pressure decay was compared for the meshes considered, and the medium grid was chosen. So the solver was ANSYS Fluent was used to solve, and a turbulence model considered was Spallard-Alamus turbulence model. The Spallard-Alamus turbulence model was chosen from reviewing the literature. It was found that this Spallard-Alamus model was more stable compared to other models in the case of subsonic jets, and it was also proven that when compared to the other two equation models, okay, the two equation models usually over predict the jet flow characteristics when you are dealing with subsonic jet. So SA model, that is Pallard-Alamas model, is more apt for subsonic jet. So thus the SA models, Pallard-Alamas model, was chosen for this analysis, and the operating conditions considered were Mach 0.4, 0.6, and 0.8. The corresponding pressure value of the total pressure value of the Mach numbers were given as the inlet boundary condition, and for the exit boundary condition, the ambient pressure and the ambient temperature was given. So I'll go into the results and discussion. So this graph presents the centerline pressure decay at Mach number 0.4. So this is a comparison of centerline pressure decay between the base nozzle and the nozzle with vanes. Okay, so base nozzle is the nozzle without any vortex generators. So on the y-axis is the gauge pressure ratio, that is the inlet total pressure, sorry, the exit total pressure ratio minus the ambient pressure divided by the inlet total pressure minus the ambient pressure. So this gives the gauge pressure ratio, and the pressure value is measured or from the exit of the nozzle along the downstream. If you can see here, the constant line denotes the potential core region. As I said, if you are increasing the mixing process, it means that the potential core region will get reduced. So a decrease in potential core region means that the mixing process has been enhanced. So if you can see here that the nozzle with vanes, okay, the potential core region is less compared to the base nozzle. So for base nozzle, the potential core region is 5D, that is 5 times the diameter of the nozzle. And the nozzle with vanes, it is 3.8D. So it is able to give a reduction of 24% in the potential core region. And after that also, if you can observe from the graph here, the zero value denotes that the jet has reached the atmospheric condition. Okay, so the jet from the nozzle with vanes has reached the atmospheric condition sooner, but if you see the base nozzle, it has not yet reached the atmospheric condition. It is having somewhat about 20% of the pressure of the that is 20% of the inlet pressure, that is somewhat greater than the atmospheric condition. It has not yet reached the atmospheric condition. So meaning that the mixing process, it has much more mixing to take place. But the nozzle with vanes has already reached the atmospheric condition, which means that there is an improvement in the mixing process. So this is the centerline pressure decay graph for Mach number 0.6. So there is the same trend, which is you can see for Mach number 0.4. Okay, the same thing is being observed in Mach number 0.6 also. Here the reduction in potential core region was 25%. So the nozzle with vanes was able to reduce the potential core region by 25%.
Balami, you have 2 minutes left here.
Okay, yeah, I'll go fast. So again, this is the centerline pressure decay graph for Mach number 0.8. So the trend is again similar. The reduction, there is a 26% reduction in potential core region. So there is an enhancement in the mixing process. So this is the overall consolidated data of the reduction in potential core region. So you can see that nozzle with vanes were able to reduce the potential core region, which means that the mixing process is being enhanced. And this is a graph which compares the pressure decay in the radial direction. So they have been taken at different axial location. So x by d equal to 0 means at the exit of the nozzle. X by d 3, 6 and 10 so far means a different location along the downstream of the nozzle. So you can, this is the left side shows the base nozzle, right side shows the nozzle with vanes. So as you can see that at the corresponding location, that is if you take x by d3, the graph is somewhat at the top, and here at x by d3 it is somewhat at a lower value than the base nozzle, which means that it is slowly reaching the atmospheric condition faster than the base nozzle. So if you take even the x by d20 location, okay, it is only in the region of somewhere in 0.2, that is it has not yet reached the atmospheric condition. But the nozzle with vanes has already reached the atmospheric condition at the location x by d20. So what these graphs shows that the nozzle with vanes reaches the atmospheric condition faster than the base nozzle. So how it is able to reach the atmospheric condition faster? Because the mixing process has been enhanced. So next is thrust loss. So basically I said that the longitudinal placement of the vertex generators is considered because the all other vertex generators which are placed parallel to the flow, they obstruct the flow. So obviously there is a thrust loss. So I needed to calculate how much thrust loss this longitudinal placement gives me. So if you see here that the reduction is very, very less. That is, I'm getting 0.52% for 0.4, 0.87% for 0.6, and 1.05% for Mach number 0.8, which is very less reduction in thrust. So it shows that you can enhance the mixing process at the same time minimize thrust loss. So the conclusion of this study is that the nozzle with vanes was able to produce reduction in potential core region of 24%, 25%, and 26% for the Mach numbers 0.4, 0.6, and 0.8 respectively. And the reduction in thrust was just 0.52%, 8.87%, and 1.05%, which was very less value. And the centerline pressure decay and radial pressure decay shows that the nozzle with vanes reach atmospheric conditions faster than the jet from base nozzle. So this is possible only from enhanced mixing process. So it is clear that the longitudinal placement of vertex generators were able to improve the jet mixing characteristics while keeping the thrust loss minimum. But one thing is that when compared to other methods, the other methods that is in the literature, they were able to produce a reduction of like 30%, 40% reduction potential for region because they were placed parallel to the flow. So the dimensions of the vanes considered in this study can be altered, or the position, the placement, the angle. So all those things can be altered, and we can study further regarding the potential for reduction and how it enhances the mixing. So this is the conclusion from this study, and these are my references. So thank you for the opportunity of participating in this conference.
Okay, thank you very much, Balamani. So I think we have time for one question. So if anyone has any question for Balamani, you're free to ask. Okay, so if we have no questions, thank you again, Balamani. So
Thank you.
to our last presenter for this room. Paper ID 40 preliminary studies using numerical analysis of the aerodynamic lift and drag over secondary curve.
Hi, everyone. So
Okay,
let me share my screen first.
who will be presenting here?
Laiva, Normi Laiva.
Normal Live. Okay, thank you very much. Okay, you are free to start whenever you can.
So can you guys see my screen?
Yes, you can see your screen.
All right. So hi everyone. Thank you, Dr. Farooq Fung. Pretty sure you guys are tired already absorbing all this new innovative knowledge. So I'm just gonna make a simple yet packed presentation for today. Sorry. So most of the research in aerodynamic industry are dedicated to find a new concept or design to optimize the aerodynamic drag in aircraft. Today, I would like to present my preliminary studies using numerical analysis of the aerodynamic lift and drag over Sakun ISAE. First of all, I would like to explain about the overview of my paper, which is to analyze the aerodynamic force on the generic ISAE model by using CFD simulation. The aerodynamic lift and drag of Sakun 3D modeling at different leading edge sweep angle is simulated. So the virtual wind tunnel domain is created with a free stream velocity of 50 meters per second to study the eddy flow simulation for the model under Spallet and Maras turbulence model. Lift coefficient and drag coefficient is recorded on each of the models at angle of attack 5 degree, 10 degree, 15 and 20 degree. Pressure distribution on the surface of each model is also presented. With the current ability of fly-by-wire concept, the effort to reduce the aerodynamic drag, research and interest towards the tailless design either for commercial or unmanned aircraft keeps increasing as the configuration offers many advantages such as providing performance improvement, fuel efficiency, reduction in noise, and stealth characteristics. According to Schultz, the consideration for performance and endurance of real aircraft often resulted in medium swept wings between 45 degrees to 60 degrees. However, the aerodynamic of this configuration is characterized by unsteady and nonlinear aerodynamic behavior dominated by a complex vertical flow. Hence, an adequate understanding of the aerodynamic of an aircraft is of utmost importance in aircraft design. Tailless aircraft, like flying wings, usually rely on the variation of span-wise lift distribution to ensure control stability in roll, pitch, and yaw are in order. In the case of uninhabited combat air vehicle, UCAV, the combination of vehicle shaping can often produce separation-induced leading-edge vortex flows. So the tailless aircraft, especially UCAV, not only has to survive by shaping for steel, but also by maneuverability. Its aerodynamic shape is also challenged by the complete suite of non-linear aerodynamic behavior. In this study, a generic UCAV with a 53 leading-edge sweep will be developed using Autodesk Inventor. Later, the leading-edge sweep angle will be modified into 45 and 60 in order to study the effect of leading-edge sweep angle on aerodynamic lift and drag with various angles of attack. The 53 leading-edge sweep angle will be used to validate the CFD code in ANSYS software before proceeding with the other variation of leading-edge sweep angle. For the model setup, SACON, which is an abbreviation for Stability and Control Configuration, is a generic UCAV model where the basic design was developed within NATO Science and Technology Organization, ABT 161 Task Group. The platform of SACON, which you can see at the first figure here, can be described as a lambda wing type and has a leading edge sweep angle at 53 degrees. The reference model layout used in this study has a wingspan of 1.54 meter and a root chord of 1.06 meter is referred from Huber and others. So, as you can see from the second figure, the main section of the model are the fuselage, wing section, and a wing tip, and its configuration is defined by three different airfoil profiles at each section. At each section, and the outer wing section profile has 5 degrees of washout about the leading edge to reduce the aerodynamic loads and to shift the onset of flow separation to higher angle of attack. So here is the 3D model of SACON with 53-degree leading edge sweep angle and the specification dimension of SACON that obtained from the NATO Research and Technology Organization Task Group. Despite of performance and endurance consideration were used medium swept wing, which I mentioned earlier, is 45 to 60 degree. Reported for UCAV radar cross-section, RCS mostly use sweep in between 50 degree to 60 degree, resulting into pure deltas, diamond, and lambda shaping. This is due to reduce the large front and side projection and remove the fuselage using intersection prone to become strong RCS corner reflectors. So in this study, leading edge sweep angle of generic SACON is modified into 45 degree and 60 degree, as you can see in this slide. The other dimensions were maintained as in the previous table. So since the span length was maintained constant during leading edge sweep angle modification, it resulted in the changes of the width of the code tip, as you can see in the first table in this slide. Table below shows the platform view for each model. So as you can see at the 45-degree leading edge sweep angle, the code tip width is bigger and smaller at 60-degree leading edge sweep angle when you compare with the Model 1. The same with the surface area. Model 2 has small surface area compared to reference Model 1, and Model 3 has bigger surface area than Model 1. So in this slide, by maintaining the span length, the effect of leading edge sweep angle modification affect the aspect ratio of the SACON. For the simulation setup, it follows the standard CFD workflow simulation using ANSYS Fluent software. So as a startup, a virtual wind tunnel is designed as a closed domain based on NASA Langley 14 by 22 foot subsonic tunnel to replicate the experiment of Sakun in a wind tunnel. Only single side of the Sakun wing model is simulated to reduce the complexity and computing time, as you can see in this figure. So after that, the virtual wind tunnel and half Sakun were meshed with the size of 0.15 meter and generated with tetrahedral shape and unstructured grid. This is to allow the solver to automatically generate the meshing parameter during meshing that helps reduce the complexity of the computational domain. The figure above, this figure, shows the final mesh concentrated of the Sakun model, and beyond that is automatically set by the solver. So for solver, Reynolds average Navier-Stokes runs is choose and Spallet-Armaras for the turbulence model because both models are widely used in the Sakun research community. Hence, show the ability to cross-reference with other model and comparable with experimental result. The table here shows the parametric value of the model and the initial condition for the simulation. So for the final point, this figure shows the aerodynamic characteristic behavior of the model configuration. Figure 1 and 2 is the lift and drag coefficient variation with angle of attack. The overall lift have a similar trend for all leading edge, only the model 3 configuration shows a lower lift for every angle of attack. This is due to the configuration is between few deltas, diamond, and lambda shape wings. The drag coefficient shows much more sensitivity due to the change of leading edge sweep angle, especially at 20-degree angle of attack for each model. Model 1 shows higher lift and drag coefficient at 20-degree angle of attack. From figure 3, Model 1 indicates better lift to drag ratio at lower angle of attack and showing an average ratio between Model 2 and Model 3 at higher angle of attack. In terms of higher angle of attack, Model 2 shows better efficiency as compared to other models. Notice that the changes of leading edge sweep angle affect the effectiveness of aerodynamic characteristic of the aircraft configuration. Last but not least, this is the pressure distribution contours on the upper wing surface of each model with a variation of angle of attack where the pressure distribution is gradually increasing as the angle of attack increases. So all the models shows the fairly pressure distribution at lower angle of attack. Later at 15-degree angle of attack, Model 1 and Model 2 start to create higher pressure at the wing tip and fuselage body. Meanwhile, at 20-degree angle of attack, Model 1 start to create large pressure distribution. This is due to the flow condition at this angle are no longer remain steady, whereas the progression of vortex breakdown start to establish. Reported by Velspin, the flow around the Sakun model at 53-degree leading edge sweep angle shows the existence of a vortex which is split into two by the effect of the boundary layer. This occurs over a small range of angle of attack 10-degree to 15-degree approximately, as the vortex onset and breakdown location move upstream. The main source of this flow distribution behavior is due to the variation in leading edge sweep The main source of this flow distribution behavior is due to the variation in leading edge geometry and the wing washout. However, with the modification of the leading edge sweep angle to 60-degree, which is model 3, it shows a better pressure distribution for entire angle of attack in terms of pressure distribution. So as a conclusion, the overall goal is to determine the effect of leading edge sweep angle modification on aerodynamic lift and drag using numerical approach. It can be concluded that leading edge sweep angle has effect on the aerodynamic lift and drag of the aircraft configuration. So from this study, it is now understood the reason of the selection of leading edge sweep angle of Sakul UCAV to be 53 degree by NATO Research and Technology Organization Task Group AVT 161. The end product of this study should greatly increase a need of further analysis in terms of flow field vorticity effect and the needs of pressure coefficient distribution in each section along the root cord. That's all for today. Thank you.
Okay, thank you very much, Nurmilaiva.
Yes.
Okay, so I will now open the floor if anyone wants to ask question to Nurmilaiva.
Yes. Hello?
I have a question.
Okay, sure.
Why did you say that the model 2 and 3 has larger wing area than a larger overall area than the model 1? Since you did not change any of the chord, just change the sweep angle. It's supposed to be the same.
No, I keep the wingspan constant. So when I change the leading edge sweep angle, the surface area for 45 degree is smaller than the model 1, and for the model 3 is bigger than
Yeah,
model.
so yes, suppose if you even if you maintain the wingspan, okay, if you did not change any chord of any parts, for example the middle chord and then the root chord and then the tip chord, if you do not change anything, the wing area will still be the same. It will not change. Do the math.
Because I created this using Autodesk Inventor. So by using the same profile and changing the leading edge sweep angle, the surface area is changes.
That is probably if you consider the curvature of the surface area. Yeah, probably yeah.
Yeah.
But if you talk about plan form area, it's supposed to be the same.
Okay, I will check on it.
If you slice the wing from the root until the tip, if you slice it, okay, thin slice, you can just rearrange into any angle. You can still have the same area.
Yeah, probably I can do that.
It's supposed to have the same area. No, I'm also doing research similar to what you're doing.
Okay.
Yeah. My students also taught the same thing. They say the wing area for the 60-degree sweep angle is higher, but that is probably because of you look at the wing is quite long, but actually it's thin, that's quite thin. But reality is the chord of the wing that is heading towards the windward chord. It's still the same. It's still the same. So the area is still the same. Planform area. If you want to create to study the aerodynamics, you have to refer to the planform area, right?
Yeah.
Yeah, it's supposed to be the same. And in fact, the aspect ratio is still the same. It won't change. Your wing area is the same. Your span is the same. The aspect ratio is the same. It won't change.
All right.
I perhaps you may check it again.
Yeah,
I may be wrong.
I may check because the only constraint during this 3D modeling is the wingspan. That's the one, and the
wingspan is constant. Yeah, you can play around with the wing sweep, but you as long as your wingspan is constant and your chord is constant for each section is constant, then you will still have the same wing planform area. Check balik Eddy, eh?
All right, will do. Thank you.
Okay. Right.
Okay, is there anyone else? Okay, then. So thank you again, Nur Malaiva.
All right.
So that ends the session for room 2 today. So for now, I would like to request for everyone to on their camera, so I would like to take a photo. So if anyone can on the camera, I would like to snap a photo first.
Dr. Farouk,
Yes.
saya nampak
Tak nampak.
saya tak buka kamera eh? Oh, kejap.
So can everyone on the camera while I just like to snap a short photo for copy. I'll give you a few seconds. Dr. Diza boleh buka tak tu?
Driving lah, I don't think I can.
Tak apalah. I just take what I see here. Okay. Okay, then I just take whatever I see here. Okay. Okay, thank you very much. So this ends the session for room 2. So there will be no closing ceremony for this conference. So we'll close it here straight away. Yes, I would like to thank everyone for participating in this conference. It is the first conference that AeroLab has actually held, and we plan to keep it up for the next few for the coming years. Your certificates will be given to you after this event. So in next week, you will receive a certificate on the condition that you have paid your fees. So again, I would thank you all again for participating. So any information regarding your papers will be informed to you through email. And is there any questions anyone would like to ask first here regarding this conference? Okay, if there's none, then I wish you all the best, and I thank you again, and hopefully we'll see each other again in the future. Okay, thank you very much, everyone. I will now
Thank
close.
you, Dr. Farouk.
Okay, thank you, Dr.
Thanks,
Rizal. Thank you.
Thank you all.